and this thing, then re-radiation from the refractory wall, and then the convection. So these are all the heat transfer taking place, and this heat transfer takes place to the outside of the tube, and then the heat goes up from the outside to the inside, and that is also very important. And that is why the tube metal temperature comes into the picture. If we have coking inside or if we are scaling on the outside, we could be having high tube metal temperature and inefficient heat transfer. That is why the tube metal temperature is most important. And then the heat to the fluid is transferred by convection. That's typically how the convection heat transfer takes place inside whatever oil or gas we are flowing will be taking place. So Firebox has three functions, major functions. Uniform heat distribution. You want all the tubes to be heated uniformly. It is easier said than done, and that is why we have so many problems in the fired heaters today. No flame impingement. So that is also one of the important parameters. Complete combustion. And some of these last two things have been amplified because of the use of low NOx burners. Whenever we use low NOx burners, our flames become very, very long. And once the flames become very, very long, we had flame impingement problems and incomplete combustion taking place. So after combustion started taking place in the convection section. So to some extent, ultra low NOx burners can be responsible for at least two of the three problems in the fired heaters. So how can we have uniform heat transfer? One way is use minimum number of fluid passes, use more burners, optimum H by D or H by W ratio, that means height to width ratio or height to diameter ratio. Have good combustion, you control the draft, control the excess O2, and also you do routine firebox inspection. So these are the operating, the last two are kind of operating. The first three are basically the design, and the last three I can say is by operating. So these are the two ways of achieving good design, good operation for uniform heat transfer is what we want to achieve. So when we are designing fired heaters, there are several ways to design it. And one of the, if you want to achieve uniform heat transfer, is to not make it very tall and narrow. I don't have to explain this, but anytime you make tall and narrow heater, you will have a lot of heat transfer in the bottom and very little heat transfer in the top. So the ratio is considered 2.5 for the VC, and similarly for the cabin heaters. What are we gaining? If we make a wider firebox, we get uniform heat transfer. What are we losing? It becomes a little bit more costly. We need more area, as well as it becomes a little bit more expensive. So you have to kind of decide where you want to be. So one of the problems what we have seen in cabin heaters is pass imbalancing, and what we have seen in that the two passes on the top are running very cold and the two passes in the bottom are running very hot. So that happens pretty often. And what we feel is if you have that type of problem, there are many ways of solving it, but one arrangement is called nesting of the passes. So the two passes, they travel together. If you can see in the third over here, basically the passes are traveling together, and that kind of ensures uniform heat transfer or uniform heating of passes, that all the four passes will be uniformly heated. So that is one way of solving if you have a non-uniform heating or pass imbalance to reconfigure the coil like this design. So here is a question for you. What is the typical average radiant heat flux in a boiler? Uh, why don't we take a guess? Well, let us see what, I think people are still typing it out. All right. The typical average radiant, these answers are good for fired heaters, but in boilers, we go anywhere between 40,000 to 80,000 BTUs per hour plus foot square. That is how high flux we go in the boilers. And why do we go that? Because we know it's not going to coke. And also we know water is an excellent heat transfer conductor. So because of that, the fluxes are very, very high. But in fired heaters, we are processing hydrocarbons, and hydrocarbons can coke or crack. So all those type of things kind of limit us to around 10,000 BTUs per hour foot square. And those of you who do not know what the flux is the heat duty per unit area, like in terms of BTU per hour plus foot square or kilocalories per hour plus meter square, And why do we limit it? Because we have a restriction on film temperature, coking, and run length. You don't want to be decoking your heater every year because it's going to, you will have to shut it down and for 3, 4, 5 days, and you will have a lot of production loss. So the general guidance is lower radiant heat flux is better for you. So these are the reader's questions. These questions we have compiled from our participants. And you can see most of them are talking about how to increase the run length, how to increase the tube life, how to eliminate hotspots, how to prevent flame impingement, how to reduce TMTs. So as I see, there are lots and lots of issues on gradient section operation or design, and it can make a big difference in the having a successful heater or a problem heater. So as we said, high tube metal temperatures is a very common issue in fired heaters, flame impingement, overfiring. Low flows can lead to coke buildup, and typically 1/8 of an inch of a coke can add up to about 100 degrees of TMT. So that is how fast TMT can go up when you have coke formation. So one of the secrets, I should say, of having a good fire heater is keep your flames away from the tubes. As we learned in the very beginning, the radiant heat transfer does not need a medium. So it travels in straight line, and Stephen Boltzmann equation, it's basically proportional to the absolute temperature raised to the power 4. So the burner to tube clearance is a very, very important parameter. If you have a lower clearance, you will have a much higher chance of flame impingement. And this has been aggravated with the ultra low NOx burners. I want to tell you, when Lobo and Evans were doing research in 1939, the burners used to be all premix burners, just the type of burners what you have in your home, gas burners. And the flames used to be very, very short. So they made an assumption of uniform heat transfer, or CSTR model, continuous stirred tank reactor model actually. Now, audio? Hello? So if so API 560 standard has been providing minimum burner to tube clearances, and those are followed. But in my opinion, they are not enough. You need to be going higher than what API 560 provides. So we have developed a technology called inclined firing technology, and it is very, very simple. We are putting the burners at an angle to keep the flames away from the tubes. We put burners at about 6 to 7 degree angle. And by doing this, as you can see in this picture, the burner flames move away from the tubes. And we have seen uh, temperature reductions of anywhere between 100 to 200 degrees F. It's a very, very simple technology, uh, and it is especially suited for low NOx and ultra low NOx burners, and it takes care of the high tube metal temperatures, which is the biggest problem in fire heater. So if you have any issues on high tube metal temperatures, we can always evaluate your heater and recommend you inclined firing technology. Very, very simple technology and very, very good. I think it should be used in all vertical cylindrical fire heaters, definitely, if not all. And as you can see, all we are doing is putting these burners at an angle. And we can use existing burners, we can use uh, new burners, and we can incline the floor, or we can use the same floor. But that's all what we are doing. We are not. And by doing this is very important. For every 10 foot of flame length, we get another extra foot of clearance. So if you got a 15-foot flame length, the flames move away by 1.5 feet. And this is very, very important, especially in old, tight heaters. That's what we. This is an example showing uh, for a 8-burner system, when we put it at 7 degree, how the clearance goes up from 6 feet to 9 feet by about 25 foot. We assume the flame is about 25 foot. This was a 65-foot box, vertical cylindrical crude heater at one of the Texas refineries. And you can see how we are able to deflect the flames away from the tube. And this does not affect any heat transfer. That's a good news. That your heat transfer still remains the same, as I said. So here is a question for you. What happens when the tubes coke up? Are you all able to hear me? I think I'm really impressed. Most of you have really covered the TMT issue, the pressure drop issue, the overheating, tube rupture, reduction in heat transfer. So thank you all for contributing. Very good answers. And my slide also shows the same, so there is nothing more to add. Tube metal temperature goes up, pressure drop goes up, firing rate goes up, firebox temperature also goes up, that's efficiency goes down, throughput starts limiting, and ultimately you have to shut down the heater and clean it. So coking is something, you don't want to have coking in your heaters actually. And this is showing a tube metal temperature profile for a clean tube and a foul tube, and you can see clean tube is around 950 and coke is adding another 200 degrees, so the metal temperature has gone up to 1150, just by eighth of an inch of a coke or quarter inch of a coke can go that, you know. So we looked at so many heaters. We looked at so many crude heaters, vacuum heaters, uh, coking heaters, coker heaters, and we kind of developed a coking index because so far all the heaters, what we talk about, don't talk about the coking tendency. So when you're buying a heater, you don't see how fast it's going to coke up. So we looked at and we said, what are the parameters you need to be focusing on, especially if you are buying a heater. If you are buying a heater, what are you looking at? You're looking at average radiant heat flux, mass velocity, coil inside diameter, burner heat release, burner to tube distance, and burner air side pressure drop. And basically, these 6 parameters can tell you, even before you're buying a heater, whether it is going to be coking or not, or how fast it will be coking compared to the relative other designs. So we are still looking at it, but if you have a heater, you're having coking issues, you can send it to us. We can evaluate and tell you what will be the coking index for this heater and how you can reduce the coking. We have designed heaters where we have designed them for 8 years run length of crude and vacuum heaters. We did it for a refinery in Lake Charles. So, and it kind of worked for 8 years. So basically, the coking has never been talked about during the design. Most of the people make sure that whatever the licensor has specified is taken care, whatever the engineering company has specified is taken care, or whatever is the API specifies is taken care, but they don't talk about, hey, is it going to coke in 2 years or is it going to coke in 6 years? And that's where I think you need to be, as a buyer, as a specifier, you need to be looking at some of these parameters to see, am I buying a heater which will coke in 2 years? Will I look good? That's what we can't kind of thing. So I have these 3 designs of a heater, crude heater. Actually, this is a real situation. And we designed it using 3 different H/D ratios. And they all meet API. So if you look at this heater, this one has a coking index of 13, and this one has a coking index of 26. What it means is this heater will coke at twice the rate. If it's 26, this will be coking. If this cokes in 3 years, this will coke in 18 months. Or if this cokes in 4 years, this will coke in 2 years. Now, the question is, if you look at the cost, anyway, you are paying a little bit extra for the heater. But if you look at the cost, one shutdown will cover more than the difference between the what you are saving. So look at the long run and see if you are buying a reliable heater or not, actually. And coking index can tell you even before you operate the heater how good this heater is going to be. So that was our coverage on the radiant section. We will cover the convection section now. So we have a small quiz for you. Convective heat transfer takes place by well, I think we got most of you got correct. Bulk movement of molecules. That's the convection. The velocity of gases is basically what is uh, transferring the heat in the convection section. So the shield section is the section which is at the inlet of the convection section. And it's also known as shock section. That's where the maximum heat flux or maximum heat transfer rate is experienced. And it's basically where both radiation and convection heat transfer is taking place. So it's a very, very critical section. And a lot of times it has high tube metal temperatures. It may have coking. It may have tube ruptures. It happens pretty, you know. So the function of convection section, is recovering heat from flue gases and improving the efficiency of the fired heater. And we are able to recover almost 20 to 30% of the total heat duty in the convection section. That's how important the convection section is. This picture shows the convection section on top of a radiant section. So basically that's how the convection section looks. Convection section has 2 major sections. We call it the shield section. The bottom 3 rows or 2 rows sometimes are called shield section. And then we have the extended surface. Shield section are bare rows, no fins or studs, and extended surface section are basically studded or finned rows above the bare tubes, and that's where the heat transfer is taking place. There have been a lot of improvements in the convection section. And the biggest is we can do the modularization of convection sections. And that has been possible because of the use of fin tubes or studded tubes. They basically made the convection sections very compact. And once the convection sections became very compact, we could make them in the shop and their costs came down And once the cost came down, we were able to transport them and then install it almost like a Lego, one on the top of another. So that's basically how the convection sections are fabricated. It's basically showing you the casing, refractory tubes, intermediate tube supports, header boxes on both sides where the return bends are housed. So that's typically the layout of a convection section. So as I said, they all used to be bare tubes. And then we started with studded tubes. Studded tubes are mostly used for oil firing. But now everybody has changed over to gas firing. So fin tubes are used in most of the convection sections. So again, a small quiz for you. Convective heat transfer goes up with higher flue gas velocity, lower flue gas velocity has no effect. All right, so most of you got it correct. Higher flue gas velocity means higher heat transfer rate or higher convective heat transfer. So this is basically showing you the convection section layout. This is the radiant section over here, shield section here, convection section, extended surface tubes over here. In the convection section, 85% heat is transferred by generally by convective, and about 15% heat is transferred by radiation means. So there is a radiation heat transfer occurring in the convection section also, just like convective heat transfers are occurring in the radiant section. These are the recommended flue gas mass velocities in the convection section. Natural draft 0.3 to 0.6, induced draft 0.5 to 1. That's typically the mass velocities. So which side controls the heat transfer in the convection section? Hey, most of you got it right actually. Flue gas controls the heat transfer in the fired heater, I should say, not just in the radiant section, not just in the convection section, but in the complete fired heater. So it's a flue gas side which is controlling the heat transfer in fired heaters. And just remember that. So that is why when we